Right, I've got to talk to you about discrete random variables. Right, let's be honest, this is not the best topic in mathematics. I'm sorry for all you discrete random variable lovers out there. I'm sorry for all you people who love probability. I don't, to be honest, I really don't. Probability is something that I just don't like doing. When it comes to teaching probability, it's like, oh I don't want to do this. But on the positive side, probability is still better than any other non-mathematical subject. You know what they are. I don't have to list them all out. You know what they are. Okay. So I'd still rather be teaching this than any other subject, if I'm honest. Is that if I've got the chance to teach maths, I'd rather it be something with a bit more zing to it. You know, mechanics, for example. Great, I do love that. Okay. Calculus, oh, now you're talking. Graph sketching, algebra, all of that. But yeah, probability. So anyway, the thing to do is just think of it this way. It's needed. You need to do this for your syllabus. So let's just get on with it. Okay. And remember, it is maths, and maths trumps any other subject. Sorry if I mentioned trump there. That was not intended. Right, discrete random variables. What are these? Okay, these are random events. Okay, random variables are values that depend on a random event. Give an example of a random event: rolling dice. Okay, picking a card from a pack of playing cards. These are all events where the random, because we don't know what's actually going to happen. Okay, something that's not random, like predicting what day it's going to be tomorrow. It's not random, is it? We know what day it's going to be tomorrow. Yeah. So you're doing with random events. Discrete because they're discrete variables. I'm sure you know what discrete means. Okay, they can take precise data values only. Usually integer values, but of course when you're dealing with shoe size in the UK, it could go up in halves. They're not continuous variables, so we won't be looking at height, okay, mass, length, width, time, that sort of thing. We're looking at discrete variables only. Okay, so number of times an outcome can occur, like number of times you roll a 1 or 2 or 3, number of times you choose a king or a queen, that sort of thing. Okay. Probability distributions. You've seen a bit of this before in terms of the sample space diagrams that you might have drawn. Remember, sample space diagram shows you all the possible outcomes. Well, in this particular topic, what we're talking about, there are 3 different ways of explaining what a probability distribution looks like. And here they are. You've got what's called a probability mass function. That sounds exciting, doesn't it? Okay, but take away the mass and it doesn't sound exciting anymore, because mass sounds like we're going to do something with mechanics. Woohoo! No, we're not. Sorry, no, we're not. It may as well just be called a probability function. You'll see what those in a minute. Okay. Using a table, which is probably what you're more used to, and using a diagram, which is quite basic, really. It's year 7, year 8 probability stuff. That. Here's just a reminder of the sum of all the probabilities adds to 1. Now, what's all this bit about x equals x? This is what throws people somewhere. Well, let me just try and explain it in the simple examples I've got to show you. Now, this is a probability distribution. It's actually called a probability distribution that's uniform. It's a uniform, a discrete uniform distribution. Okay, a discrete uniform distribution is when all the values are discrete. In this case, it is because it's it doesn't say so on there, but this is rolling dice. Okay, numbers 1, 2, 3, 4, 5, 6 can come up on a single roll of a die. Okay, die is plural. Sorry, singular. Remember. All the probabilities are the same because you get 1/6 each time. When all the probabilities of something like this happening are all the same, when all the outcomes are equally likely, it's called a uniform distribution. Okay, but it's not always uniform. All right, it's just an example showing you that. Here you've got 3 different ways. Well, in reverse order, should we say? The diagram. Okay, it's pretty simple, really. It kind of looks like a line chart, like a bar chart, but with just lines instead of the actual bars. Okay, and you've got the probability on the vertical scale, so 0, 0.1, 0.2, obviously that being 0.16 recurring. And then on the horizontal scale, you've got each of the different possible outcomes. So you can roll a 1, 2, 3, 4, 5, or 6. Okay? And because they're all the same, all the bars, the lines, they rise to the same height. Okay? Sometimes that's called a discrete rectangular distribution. Okay, trying to make it sound more interesting by getting rectangular, because it already sounds like, oh, shapes, geometry. No, it's still probability. Okay. This is what the table looks like, probably what you're more used to. Yeah, that's pretty simple. Okay, but I'm going to try and use the table to explain to you what the difference is between the little x and the large x. We call it lower scale and upper scale, of course. I've got little and large, sorry. So what the little x stands for is each individual possible outcome, what could actually happen. You could have a 1, 2, 3, 4, 5, 6. So if I asked you for the probability when x equals 5, I'm talking about little x equals 5, probability is 1/6. The capital X is basically the whole event, and it includes all the possible outcomes. So when we say probability of x equals little x, we're saying really, what's the probability that of everything that can happen, it's going to be this particular case. So capital X is basically covering everything, little x is each individual one. So when it says probability of large X equals little x, it means what is it for a particular case. And that's important because the other way of describing the probability distribution is by using what's called a probability function. This is what some people find harder to get to grips with, okay? It's actually the more exciting bit because it kind of looks like it's algebra. It's not, it's still probability, I'm afraid, okay? But it's not geography, so it's like, great. Sorry, I mentioned a subject. How naughty of me. Anyway, yeah, so this is what a probability function looks like. It's basically saying that the probability that you get an individual result, such as x, is 1/6 for each of these values. 1, 2, 3, 4, 5, 6. That's pretty much it. You want to see what an exam question looks like? Yeah, I'm sure you do. Yeah, let's have a look at an exam question. Yeah, it looks a little bit like that. Hope you can read it. So, a discrete random variable x has the probability function, this. Right? So what it's actually saying to you is that the probability of an individual outcome happening is either this or this. Because remember, it's not always going to be a uniform distribution. It's not always going to be the same probability for all the outcomes. So it's more likely you've got, well, the probability could be this or this or this, depending on what the outcome is. Yeah. So when you've got the outcomes being negative 1, 0, 1, 2, the probability always obeys this rule. Now sometimes the probability is given for you, but sometimes the probability is dependent on what the actual number actually is. Okay. 0, otherwise, what that basically means is there's no other option, because the probability of 0 means it's impossible, it's not going to happen. Okay. So let's just take a particular one of these. Let's just look at 2, because it looks like the nicest number, doesn't it? Okay. I like the number 2 as well. The only even prime number. Good enough reason to like the number 2. So let's just suppose x equals 2. What we're saying is the probability is 1 subtract 2, which is negative 1, squared, which is 1 multiplied by k, which is k. That was the most exciting bit of this whole presentation so far, wasn't it? Substituting a value into an expression. Just want to point that out. Okay. So there's always something to like in probability, because like, you know, if you don't like probability as a subject, you still got, you know, yeah, that's what I do. I look at the bright side of these things. Again, it's not teaching any other subject like, I don't know, history. Oh, did it again, mention another subject. Okay. I actually do like history. Okay, well, it depends what period, doesn't it? Yeah, it depends what period in history. Yeah. But as a subject, I kind of like it. Yeah. But of course, it's not as good as statistics. There's a hierarchy of subjects, isn't there? Okay. Anyway, so if you put in x equals 1, you get 1 subtract 1, which is 0, and you get 0. That means the probability of you getting x is 1 is going to be 0. Hey, what's the question? It says show that k is 1/6. Okay. How do you do that? Well, what you do is you substitute each one of these in individually, write down what the expression is in terms of k, or if it's not, this could be 0. And then you say, well, these have got a sum to the number 1. Because all these probabilities here, that counts for everything in the distribution, have all got a sum to 1. All of them have got to happen. So what you could do is show you working a little bit like this. You don't need to use a table. This is more like what an examiner's mark scheme might look like. Okay. But for each of these, I said to you that when x is 2, you get k. I said to you when x is 1, you get 0. If you put in 0 and x is 0, of course you get 1 squared times k, which is k. When you put in negative 1, you get 1 subtract negative 1, which is 2. 2 squared is 4. You get 4k. So basically, in terms of k, these are the probabilities of each of these happening. Okay? When you add all those together, you get that plus that plus that plus that is equal to 1. 6k is equal to 1, hence k is equal to 1/6. And that's that. Okay. Hope you found that reasonable in terms of understanding it. There's another example coming up right now. Okay, let's do this one. This looks more like a full-on examination question, doesn't it? Okay. Still, much better than having to do an essay question, in my humble opinion. So even though it looks like probability, let's just get through this. I'd still rather do this than answer any long-winded question about anything involving an essay. Okay, so that's the way you look at it. Okay, it's not the most interesting part of mathematics, but still a branch of mathematics. Yeah. Actually, that doesn't beat all the other stuff, pure mathematics, for example. But it's got to be done. Yeah, it's got to be done. Okay. I ditched probability as soon as I could at university, if I'm honest. Okay, it's like I did all the compulsory units, and as soon as the probability became optional, it was like, nope, get rid of that. I don't want to see that again. And then I came into teaching and having to do probability again. Yeah, but still, it's got to be done. Okay. I call it the easy branch of mathematics. Well, one of them, statistics and probability. I call it the easy part of mathematics because it's not that difficult, really, if I'm honest. It's just not the most challenging. It just doesn't really interest me as much. Okay. Anyway, moving on to this. So, see, any opportunity I get to go off tangent, and I do it with probability. Okay. Right, let's have a look then. So, show that k equals 0.1. So you've got a distribution given in terms of a table, and the only thing you need to remember is that all of these probabilities have got it up to 1. That's it. So add these together. So 4, 7, 8, 9, 10. So you've got 10k. It's a show that question. So you can't just write down k. You really should write down, well, k plus 2k plus 3k plus 4k is equal to 10k. 10k equals 1. Therefore, k equals 0.1. And you're done. Okay, that's fine. That's all we need, really, for that. Right, so swiftly moving on. What I suggest you do is then just rewrite the table with the actual probabilities because it might help you with the rest of the question. So let's just write that as, that is 0.1, so 2k would be 0.2, 0.3, 0.4. And those are the probabilities of these happening. So swiftly onwards to part E. Well, I missed out B, C, D. I can't remember what they were actually, but obviously about something else that we don't need to do in this section. Two independent observations, capital X1, capital X2, are made of X. Show that probability of X1 plus X2 equals 4, equals 0.1. This is what throws people. The notation. What does that mean? I'll just try and break it down for you. So here's a probability distribution. Just make up something. It doesn't say what it's for, just make up. Suppose it's a tetrahedral die. That is a die made up of 4 different faces, a tetrahedron, okay, which some people might use if they play, these role-playing games. I don't, but some people would use them. Anyway, suppose, and you can get either one of these. These are probabilities of it happening. Obviously, it's a biased die, okay. So one person, let's call that one person X1. Okay, obviously they've got a name, but let's just call them X1. Okay, that person rolls this die once, and these are the outcomes they can get. They can either get 1, 2, 3, or 4. Let's suppose somebody else then comes along. Let's call them X2. And then they roll the die. Can you see what I'm getting at here? So these two people, call them X1 and X2, it could be Bill and Ben, whoever you want. They each roll the die. And from the rolls of the die, they get all of these, okay? What is this then saying? It's saying, show the probability that the score, when you add them together from the two separate rolls of the die, the score is 4. Just write down what ways that can happen. Well, suppose the first person rolls a 1. The next person has got to roll a 3, haven't they? In order for that to happen. Yeah? Or the other way around. It could be the first person rolls a 3, second person rolls a 1, so 3 and 1. And then just put down all the options, okay? You can get a 2 and a 2. In either order, of course, so just list it once, 2 and 2. But then that's it. Okay, that's it. We've already gone for the 3 and the 1. You can't have a 4 because then a 0 is impossible. So that's it. So the way of getting a total score of 4, okay, are here. We've just got to work out those probabilities and then again show that it gets 0.1. That's it. Right? And then you broke it down into effectively what's a GCSE question. So part of all this A-level stuff is actually getting to know what all of this means, what the shorthanded notation actually means. That's part of the actual challenge. Okay. So we'll just work out the probability of these. Well, let's just take these one at a time. So probability of getting a 1 and a 3, yeah, so that's 0.1 multiplied by 0.3, yeah. let's just get rid of that. So 0.1 multiplied by 0.3, because it's that probability multiplied by that probability there. And the same with that, isn't it? 0.3 times 0.1. So what you could do in shorthand is write it down as 2 multiplied by that. Okay, because there's 2 ways of getting a 3 and a 1, basically. And then for getting a 2 and a 2, it's going to be 0.2 times 0.2. You can write squared if you want, but I don't bother when it's with decimals, to be honest. 0.2 times 0.2. What you then got to do is just add those together. Obviously, you set your working out appropriately. Okay, so you do this times this times this, so that's going to be 0.03 times 2, so 0.06. We'd write that equals 0.06, obviously. And then 0.2 times 0.2 is 0.04. And then you sum those together, equals 0.1. Okay, that's it, 0.1. And then what you do is you complete this distribution for x1 plus x2. So basically it's saying, in the scenario that you've got these 2 people rolling the die, each one separately, okay, what's the probability of getting a total of 2, 3, 4, 5, 6, 7, 8? Well, we've actually done this one now, haven't we? The probability to get the sum of 4, that one there. Okay, so notice our answer, we've got 0.1 has been filled in for us. Yeah? And somebody has worked through the chances of getting all the others. So probability of getting a total of 2. Well, there's only one way of doing it. That's a 1 followed by 1, 0.1 times 0.1, hence 0.01. Can you see this one is an easy one to fill in? Because there's only one way of getting a total of 8, isn't there? You've got to have both of them getting a 4. Roll a 4, roll another 4, that's it. There's no other way of doing it. So this one is pretty easy. 0.4 times 0.4. We can fill it in now. 0.16. Yeah. And then for this one, well, 2 ways of doing it. One way is to, like we just did now, list all the outcomes, okay, to get 5. You can get a 1 and a 4, or 4 and a 1. You can get a 2 and a 3, or 3 and a 2. Okay? Work out those probabilities, add them all together. There is a quicker way though, yeah? Can you see this is the only one missing from the table? What have I said about all those probabilities? They must add up to 1. Yes. So my advice to you is when you're filling out a table, if there's just 1 left to fill in, just see what happens when you add all these numbers to 1. Okay. So let's just do that. So that gives us 0.4, 0.65, 0.75, and 0.8, 0.2. Okay. And then that's it. Always try and go for the quickest way. Right. That's one of the interesting bits, I suppose, about this sort of work. Just one of them. Okay. You can try and find quick ways of doing stuff. Okay. Then this bit here. What's all this about? What's all the inequalities business about? Because in inequalities, we usually reserve those when we've got continuous data, don't we? Yeah? Well, essentially we just interpret what this means for the discrete data. So when it says find the probability that x1 plus x2 lies between 1.5 and 3.5, not including 1.5, it's basically saying what's the probability of getting any integer value, because these are integer values, between 1.5 and 3.5. Obviously you can't have any decimals, so you're only including the number 2 and the number 3. So you're only including those, aren't you? Yep. Anything beyond that, we're not interested. So include what's the probability of getting this or this. Notice the or, okay? That same probability of x is somewhere in between us. So it's these two added together, 0.01 added to 0.04, 0.05. That's it, done. Okay. I'm hoping you found that useful. Hope you found it interesting. I'm going to try and make it a little bit interesting. Okay, it's certainly more interesting than, dare I name another topic? Oh. No, I shouldn't really. No, music. Oh God, did I say that? I like listening to music. Yes, everyone likes listening to music, and you could argue music is mathematical. I don't really like studying it, to be honest. Yeah. Other subjects? All of them. All of them. Okay. All of them. Maths is best. Okay. Anyone that comes closest is physics, really. Okay. If I really had to do something else, it probably would be physics. Okay. But then it would be from a mathematical point of view, of course. And so it's slightly biased, and so I wouldn't really make the ideal physics teacher, if I'm honest. Yeah, because I would be doing it all from a mathematical point of view. Yeah. So I've got to stick to maths really. Yeah. Right, that's it for now. There's another video coming up on something else. Okay, got to get through more of this stuff. But yeah, stay tuned. I'll try and make it interesting. Okay, I'm just going to slip this little bit in my presentation somewhere. Not sure where it's going to go yet, but it's going to go somewhere. It's about the cumulative distribution function. It's very, very simple. It's like cumulative frequency, where you just add up the frequencies as you're going along. So an example here, you've got a probability distribution set out into a table. So the probabilities of each of these individual values, 0, 1, 2, 3, are 0.4, 0.3, 0.2, 0.1. The cumulative distribution looks like this. You just add up as you go along. So the first probability, 0.4, added to the second probability, makes 0.7 as a running total. Added to 0.2, makes 0.9 as a running total. And of course, all of them must sum to 1. So it's not surprising that the last value there is 1. Incidentally, this is capital F of x. So P of x for the probability. For the cumulative distribution, it's f of x. And that's all it is. That's all I need to say about that. Okay?